Welcome to the third lecture of the lecture series on real and complex line arrangements. So the focus of today will be complex line arrangements in view of Sylvester-Gallai type problems. And in particular, I'll speak about some very special arrangements for which the Sylvester question has a negative answer. So these are due to Hesse, Klein and Wiman. And then I'll mention Hirzebruch's inequality, and here are some references for today's lecture. Okay, let's start. So there's a natural extension of Sylvester's problem to complex numbers. So does the Sylvester-Gallai term hold? Over complex numbers. So let me rephrase this question again. So suppose we have a type A point line arrangement in complex projective plane. What does that mean? So you begin by selecting a finite set of points. Pick a finite set of points. In complex projective plane, such that not all of them are collinear. They are not contained in a single line. Then draw all the connecting lines, and by lines I now mean complex lines, which means those coming from two-dimensional vector subspaces of C cube. So draw all the connecting complex lines. So topologically, these are CP1s, therefore they are spheres. Okay. Is at least one of them ordinary? At least one of them necessarily ordinary. That means it contains just 2 points. Contains 2 points. Does this always have to happen, regardless of the initial choice of points? As opposed to the real case, now the answer is no. There are examples, and actually those are the examples that I'll try to explain today. Okay, before going to the examples, let me mention that the proofs for Sylvester-Gallai theorem in the real case all in some way depend on the fact that the real number field is a totally ordered field. But C doesn't have this property, complex numbers doesn't have this property, so all of these proofs break down. One may also try to imitate Melchior's proof. What Melchior did was to pass to the dual projective plane in the real case, and then to study the polygonal polyhedral subdivision of RP2 provided by these lines. and then get a contradiction from there. But this doesn't work either because, well, you have duality in CP2, no problem about that. You can pass to a dual projective plane. However, this time the complex lines, which are CP1s, will not provide a polyhedral subdivision. They will just give you some homology 2 cycles inside a 4-dimensional manifold, but not a subdivision. So that's why this Melchior's proof, in a way, doesn't carry out in the complex case. Okay. Now, all the arrangements in the complex case which violate this thing, so which have no ordinary lines, turn out, I mean, the examples known so far tend to have very special geometry and a lot of symmetries. Okay, so I start from the so-called Hesse arrangement. Okay, so to explain this, we start from a cubic inside CP2. Consider a smooth cubic. So what does this mean? This is defined by a homogeneous third-degree equation. So something like f x y z equals 0. It's a cubic polynomial. And homogeneous. And the smoothness condition says the partial derivatives don't all simultaneously vanish at a point on the curve. So this gradient f is not the 0 vector at any point on C. Okay. Now, the points of a smooth cubic have the very important property that they have a group law. So we talked about this a little bit in the previous lecture in relation to real cubics, but this also holds over any field. So the points of C satisfy group law. So, okay, what I'll draw is a real picture. However, one should think about this happening in the complex projective plane, only I cannot draw that. So the group law is, okay, suppose you have 2 points on this cubic, and assume that the cubic is placed such that it's in so-called Weierstrass normal form with an inflection point at infinity. So inflection point at the point 0, 1, 0 at infinity, which will play the role of the identity element in this group. So addition law is as follows. So draw the straight line through PQ. So that line will intersect your cubic at the third point, and then take the mirror image of that with respect to x-axis, that will be your p plus q if your cubic is in Weierstrass normal form. Okay, so there's a very explicit group law. Now, what happens if p is equal to q, so if the 2 points coincide? Let me draw another picture. Here, for example, let's say this is r, and let's try to find r plus r. Well, one can imagine that if q comes close to p, then this line will become a tangent. And indeed, in order to find r plus r, one should draw the tangent line to the curve at r, and then reflect this point. So this will be 2r. And there's also one more thing to mention. There are some special points of this curve called inflection points. These are the points of C where the tangent line intersects C at order. So these are the points where tangent line intersects C with multiplicity equal to 3. In general, the definition is to intersect with multiplicity at least 3, but since it's a cubic, this is all you can have. And for an inflection point, if and only if 3p is equal to 0 with respect to group law. So, okay, you do this intersection, but suppose that R is not just a tangent, but it's an inflection point. So the third point will be itself, and that implies eventually that 3p must be equal to 0, and the converse of this is also correct. Now, there's another way to think about this. Okay, this is supposed to be some complex cubic, so it's defined by one complex equation, therefore two real equations. So it gives you some two manifold inside CP2. But which two manifold? Now, by the degree genus formula, genus of a smooth curve of degree d inside CP2 is given by 1/2 d minus 1 d minus 2. And since we have d equals to 3 now, this will give genus equals 1. So as a two manifold, C is a genus 1 orientable surface. That means it's a torus. So I could draw this familiar picture, but bear in mind that this torus sits in a rather non-trivial way inside CP2, kind of going all over the place. Okay. Now, there is another way that you can construct a torus. That is by taking a quotient of the complex numbers by a full rank lattice. And so is as C mod lambda, where lambda is a rank 2 lattice inside additive group C. And then actually, it turns out there's an explicit map from every smooth cubic curve to such a lattice and backwards as well. So picture is roughly as follows. You have your complex cubic here, smooth cubic, and you have C mod lambda here, which I could try to make a picture of. So you have your lattice here. That means you have some additive subgroup of additive group of complex numbers. So that means you have vectors in two directions like that. And okay, let's look at one of the fundamental regions. So every point in the quotient will be represented by a unique point in this parallelogram. Now there are maps back and forth which are holomorphic. If you want to go this way, this is given by the Weierstrass P function and its derivative, or if you're in homogeneous coordinates, you could include here a 1. Well, if you are looking at the lattice point, send that to the point at infinity. That's an exception. But for all other points in the parallelogram, this is the map. Here's the Weierstrass P function. And the map in the other direction is given by periods of holomorphic forms. So periods of a holomorphic form. And then the nice thing is the group law on the cubic is just given by the ordinary group addition here. So these maps respect group law. So for example, if you want to find the inflection points, you have to look at those points here which satisfy 3p equals 0. And in the additive case, that's quite easy to spot because you just want to find those points here which satisfy 3p equals a lattice point. And there are exactly 9 of them. They are the 3 torsion points of this abelian group. So there are exactly 9 such p. So in particular, this whole picture implies that there must be 9 inflection points of any smooth cubic inside CP2. Let me write that. So any smooth cubic in CP2 must have 9 inflection points. One can also see this directly without making reference to the period map or the Weierstrass P function. Okay, what one has to do is, if your curve is given by f equals 0, so C is f equals 0. So the question is, how do you spot the inflection points by looking at the polynomial? Well, you have to construct the so-called Hessian. So Well, you do take second derivatives of f with respect to your coordinates, and then take the determinant of this matrix. Let's note that f is third degree 3, therefore second derivatives are linear. So you have a matrix of linear polynomials. It's a 3 by 3 matrix. And once you take the determinant, this is going to be a cubic itself. And the inflection points are precisely the intersection points of these two cubics. So these are f equals 0, intersection g equals 0. You have two cubics intersecting in CP2. So by Bézout's theorem, you expect 9 points. But one may wonder, maybe, do you really get precisely 9 honest points, or is there a multiple intersection? Well, this argument shows that all these intersections must be transverse, and you have 9 points, but that you could also check that directly. Okay, now, what does this have to do with line arrangement? Okay, now consider the set of all 9 inflection points. Consider the 9 inflection points as your point set. Now, if P and Q are inflection points, and let's say R is maybe 1, maybe not a priori, but let's say it's on the same line with PQ. On the line PQ, intersection the cubic, that's one more point, right? So let that be R. Now, let's see what happens. So since they're all collinear, by group law, the sum must be 0. Therefore, just multiply everything by 3. This must still be 0. But P and Q are assumed to be inflection points. So these are 0. But then this tells you that 3R is 0. So R itself must be an inflection point. And the consequence of all this is that if you draw on a cubic, on a smooth cubic, if you draw the line through any two inflection points, then the third intersection is automatically an inflection point. So the line through two inflection points passes through a third. Okay, that's important consequence. But now for the line arrangement, it means that if you start this with this 9-point set and draw all the connecting lines, then there are no ordinary lines, because each of these lines exactly contains 3 points. So the corollary is this set of 9 points with its connected lines has no ordinary lines. So in previous lectures notation, T2 is equal to 0. Okay, I can sort of draw schematically what this looks like. So you have 9 points. Of course, this is not going to be an honest picture, since I cannot really draw complex lines in CP2 on the board. But if I could, it would look like this in a sense. So you have these lines containing these triples, then other lines containing such triples, then also some more. For example, the line through these two should pass through a third. The line through these two should pass through a third. Although these don't look like lines here, if I really was able to draw lines in CP2, they would be honest complex lines. And so similar here. So altogether we have 12 lines. And they're all containing 3 points, therefore T3 is 12. So yes, so this is a complex arrangement with T2 equals 0, T3 equals 12. By the way, this picture also coincides with the finite geometry of the affine plane on a 3-element field. So this picture coincides. If you're interested in finite geometry, this is affine plane or a finite field with just 3 elements. There are various ways to say this, I guess. You could put this matroid inside CP2 or as an embedding. That's another way to say it. Okay, before we go on to other arrangements, maybe a couple of words. One thing which is known is, okay, this is the Hesse arrangement. Let me repeat. Okay, one thing which is well known is the Hesse arrangement is unique up to projective equivalence. That means if you started with some other elliptic curve, some other cubic curve, and did the same thing, okay, apparently you have different points and different lines, but there's an overall projective transformation which brings you back to this one. It doesn't matter which cubic curve you start with. And even abstractly, if you think you found such a configuration inside CP2, maybe without reference to any cubic curves, again, there's a projective transformation which brings it to you this one. Okay, so that's all about Hesse arrangement. So let's talk about another one. Okay, the other is so-called Fermat arrangement. So this is actually an infinite family. It's not just a single arrangement, but there's a parameter. So we'll describe this in the dual case, so in the type B setup. So recall that this means instead of starting from points and connecting lines, we start from lines and draw all the intersection points. Okay, it's a little bit easier to say it that way. So let now n, in this case, it's going to be the number of lines instead of points, right? So the number of lines here will be, let's say, 3 times d. So, and the n lines of the type B arrangements are precisely these. I'll just write a single equation, but the factors will give the lines. So x to the d minus y to the d, y to the d minus z to the d, z to the d minus x to the d equals 0. So this is on the face degree 3D polynomial, but of course there are many factors here. So each of these factorizes further into linear pieces. For instance, x to the d minus y to the d is equal to a product of x minus zeta to the a times y, a running from, let's say, 0 up to d minus 1, where zeta is a primitive d root of unity. So I could choose e to the 2 pi I over d, or for any other primitive root for that matter. And similar for the other two factors. So it completely factorizes into linear polynomials, and they're all distinct. Therefore, you get 3D lines overall. And of course, we're using essentially that we're in the complex field in order to be able to get these complex roots. Okay, so where are the intersection points of these lines? So in order to understand the geometry, we have to find them. Unfortunately, they are quite easy to find in this case. So the intersection points of lines. Well, you can do two things. You can have two lines with using the same variables, for example, x equals zeta to the a, y intersect x equals zeta to the b, y, a not equal to b, let's say. What's this point? So if both of these happen at the same time, then these should be equal to each other. But that would imply this equality? Well, by the choice of A and B in this range, these powers are distinct there. Since zeta was a primitive root, all the D powers are different values. This is not 0, so y is 0. But if y is 0, x is 0 as well. So there's only one such point in the complex projective plane. So the intersection is the point with homogeneous coordinates 0, 0, 1. But this is true for any such AB, and there are D such lines which involve just X and Y. Therefore, the 0, 0, 1 lies in intersection of D lines. Okay. And it's a similar story for 1, 0, 0 and 0, 1, 0. So 1, 0, 0 and 0, 1, 0 each lie in the intersection of D lines. That's good. Now, we also have these other pairs of lines. One, let's say one involving X and Y, the other with Y and Z. So let's look at that. X equals zeta to the A, Y, intersect, let's say Y equals zeta to the B, Z. This is also quite easy to spot. Well, if Z were 0, then Y and X would also be 0, but 0, 0, 0 is not a point in projective plane, so that doesn't work. So we can set Z equals 1. But then Y is equal to zeta to the B. And then you can figure out the value of X, zeta to the A plus B. So there's this unique intersection point, right? And any two lines should intersect in one point anyway. And also in the third class of lines, there's one which passes through this one. So this is also on which line? X equals zeta to the A plus B Z, right? So through there are three families of lines, so to say. If you take one from the first family and one from the second, there's a unique line in the third family which passes through this point. And this says all of these points are triple intersections. So all points like, let's say zeta to the C, zeta to the B1, all points of this form are triple intersections. Okay, then we can make a count. So how many triple intersections are there? So you can put here any D roots of unity that you like. Therefore, there are D square such points, triple points. And we found out 5 minutes ago that TD is equal to 3, and all other values are 0. So again, please notice that T2 is 0. Therefore, there are no ordinary lines in this picture. T3 has a large value, and you also have TD equals 3. So this is an infinite family of arrangements, one for every D, where T2 is equal to 0. Maybe a remark. In the case D equals 3, what happens? Well, you have 9 here, but also this is T3. So you have 3 extra points. So altogether it makes 12. T3 is equal to 12, which actually agrees with the numbers of the Hesse arrangement. And indeed, that's projectively equivalent to Hesse arrangement, or the dual of the Hesse arrangement, because we're in type B, but you get back to Hesse arrangement for D equals 3. Okay, let's start the second part. So we are speaking about special complex arrangements. So another one is a Klein arrangement. So again, I'll describe in the setup of type B. So lines and their intersection points. So this will have 21 lines with the following numbers. So I'll say something about why these are true. T3 equals 28, T4 is 21. And all other TKs are 0. So this is something highly symmetric. So I want to describe this. Now let's start from some motivation. So you could describe this in many different ways, but let's start by describing some other symmetric object just to make the discussion easier. So think about some highly symmetric objects, such as a Platonic solid inside our cube. So consider okay, this is not what we want to discuss, but this will be a starting point only. So these are, tetrahedron, cube, octahedron, dodecahedron, and icosahedron, and they come in dual pairs. So tetrahedron is its own dual. So it has triangular faces, and its rotational symmetry group in our cube, rotational symmetry group. You can find this in many ways. Well, one way to think about it, I guess, you can fix a face and think about the 3 rotations, but then you can take any face to any of the other faces as well. So you expect to have 12 elements, and indeed, it is the alternating group on 4 letters, which has order 12. For the cube or octahedron pair, I'll just draw one of them. That's sufficient because the other is its dual. Okay. This time, fixing a face, you have 4 rotations, and you can take a face to any of the other 6 faces, so you expect 24 elements. And indeed, some work shows that the symmetric group is the symmetric group on 4 letters. This time it's S4, and its order is 24. Whereas for the remaining pair, dodecahedron, icosahedron, which is harder to draw, but the dodecahedron has pentagonal sides, pentagonal faces, and icosahedron has triangular faces. Well, this time you have 5 rotations fixing a face, and there are 12 faces of a dodecahedron, so you expect 60 symmetries. And indeed, the rotational symmetry group is the simple group A5, which has 60 elements. So now the point which is particularly important for us is that, okay, these highly symmetric objects exist, but it also tells you that these 3 groups have some natural embeddings into the orthogonal group of dimension 3. Therefore, in particular, one can say that A4, S4, and A5 are subgroups of the rotation group, so SO3R, in a natural way. Okay, so in a similar sense, we want to find a certain interesting subgroup of not SO3R, but the symmetric projective symmetry group of CP2, so that's PSL3C. So in a similar we want to find an interesting finite subgroup of PSL3C. It's this group because this is the symmetry group of projective linear transformations of the complex projective plane, where our lines will live. Okay, now intuitively one could try to go on. Okay, with squares or pentagons we were able to make cubes or dodecahedrons. If you had hexagons, regular hexagons, well, the natural thing to do is to fill out a plane with that. And then in that case you cannot quite get a sphere, but you could get a torus by quotienting the plane. So let me write that too. So regular hexagons. Okay, you can fit them in a plane. You cannot take a quotient of a plane and get a sphere, but you could get a torus. That's possible. However, that's not what we are going to be interested in now. Let's go one step further. Let's look at regular heptagons, so 7 sides. So these are 7 gons. Well, you cannot quite fit them together to give you a sphere or a plane, but if you negatively curve them, if you introduce negative curvature, you can fill out the hyperbolic plane with them. There are various ways to represent a hyperbolic plane. For instance, the upper half plane model or the disk model. Let's think about the disk model. So take a unit disk with the boundary excluded. then you want to fit regular heptagons there, but due to the hyperbolic metric, the angles get smaller than their usual Euclidean counterparts in the hyperbolic plane. I couldn't quite draw it, but here's a heptagon. And it's conceivable that by arranging this angle carefully, that depends on the size of the heptagon, you can fit any number of them you like along a vertex. So let's fit 3 of them. So fits 3 heptagons on one corner and continue this. You can tile the whole hyperbolic plane. This is possible. This is explicitly possible. So very good. But okay, fine. This is tiling the hyperbolic plane. But in the previous problems, we had some compact object like the sphere or a torus. Now, what can we get this time? So the closed manifold quotients of the hyperbolic plane H must have genus. They're going to be Riemann surfaces or complex curves for that matter. They're going to have genus at least 2. So they must have negative Euler characteristics. So the Euler characteristic of an orientable 2 manifold of genus G is going to be 2 minus 2G. So for G equals 0, you get back the sphere. It's 2. For G equals 1, you have the torus, which is Euler characteristic 0. And starting from G equals 2, you begin to have negative Euler characteristic. And those, it's a wonderful result that any such Riemann surface can be obtained as some quotient of the hyperbolic plane. This is a consequence of uniformization theorem. Now, the next thing you can think is, okay, I want to use regular heptagons, 3 meeting at a vertex. So how many of them do I need in order to find some certain genus? To use 3 meeting at a vertex, let's say, just like the dodecahedron, to get genus G. There are various ways to think about that, but maybe one of the fastest is the Gauss-Bonnet formula. Which tells you that 2 pi times the Euler characteristic must be equal to the total integral of the Gaussian curvature with respect to area. Okay, now there are again 2 ways to think about your polygons. Either, as I have drawn like a few minutes ago, you can think of them as carrying curvature and with small angles. Then that curvature will be spread out along the polygon. Now you get an honest integral. Or there's an alternative way. You can think about them as flat polygons, but at the corners, they just meet in a non-smooth way, so that the curvature is concentrated at the vertices. And then the angle defect gives you the curvature. So think of, that's the easy way to think. Think of polygons as flat, but meeting non-smoothly at vertices. So then the curvature is given by angle defect. To illustrate, let me go to the test case of the dodecahedron once again before handling the case of heptagons. So. Now on the left side, we know what we should get. So it's 2 pi times Euler characteristic of the sphere, which is 2. So the total that we get should be 4 pi somehow. Let's see if we can get that. So you have your dodecahedron. Let's say this is a vertex. Let's see what happens at this vertex. Now, the interior angle of a dodecahedron is what? So it's pi minus 2 pi over 5. Therefore, it's 3 pi over 5. The three together don't quite make 2 pi, right? That's the angle defect. So the angle defect at a vertex is 2 pi minus the sum of these three angles, 9 pi over 5. Which is pi over 5. So you have a defect of pi over 5 at every vertex. Then you want to think about how many vertices you have. And in a dodecahedron, you have exactly 20 of them. So 20, this is the number of vertices. And you have an equal defect at each of them. It's pi over 5. And that's kind of Gauss-Bonnet in this setup, okay? So you think about curvature as concentrated like Dirac delta functions at these vertices, and then they add up to 4 pi. Now, let's do this with heptagons. Again, if you think about them as flat, 3 meeting at a vertex, then you'll have an angle defect. So this time the interior angles are pi minus 2 pi over 7. That means each angle is 5 pi over 7. You have 3 of them meeting, so the angle defect at a vertex is equal to 2 pi minus 3 times 5 pi over 7. So this time it is negative. It is minus pi over 7. Well, it's negative because you ought to have negative curvature. Okay, and what does Gauss-Bonnet tell you? It tells you that 2 pi times the Euler characteristic, which is 2 minus 2g, must be equal to the number of vertices v times minus pi over 7. Okay, we have this equality. Okay, instead of number of vertices, we might be interested in number of heptagons. So let's say n is the number of heptagons. But we can figure out the relation easily. Each of these will give you 7 vertices. And each vertex will be used 3 times. So n should be like 7, no, 3v over 7, right? Each n will give you 7 vertices, but each vertex will be used 3 times, so they have this relation. So if you plug this in, you have 7n over 3 times minus pi over 7. And you can cancel the pi's on both sides. Okay, this gives you the answer. N equals, there's a minus sign here, but you can flip that also. This is 12 G minus 12. So the answer is, if you want to form a genus G Riemann surface, then you should use 12G minus 12 regular heptagons. Okay, then we can look at the smallest values of G to do something. For G equals 1 is out of question, because that's not going to give you negative curvature. G equals 2, you could do 12 heptagons. This is fine, you can do this, but the problem is about trying to embed this Riemann surface into CP2. So let's see. You have a Riemann surface, you want to embed it as a curve inside CP2, but let's think about the degree genus formula once again. It's told us that genus is 1/2 d minus 1 d minus 2 for smooth curves. If we make a small table, then for degree 1 and 2, you get genus 0. These are lines and conics. For degree 3, you get genus 1. It's cubic curves that we talked about. And then 4, you have genus 3, and then it increases. So 2 is skipped over. So this tells you that a genus 2 surface cannot occur as a smooth curve inside CP2. Well, you might want to try to embed it as a singular curve. Then this formula is corrected, and that you can do that. This is possible. But then you lose a bit of the symmetry if you try to embed it as a singular curve. So that's, since we are so much interested in the symmetry, that's not what we are going to do. So what instead we do is go up to genus 3. And you can use 24 heptagons. And indeed, you see that it's possible to embed it as a quartic curve. And there's a little bit more, actually, side of the story. The theory of algebraic curves tells you that it's not just these can be embedded, but every genus 3 Riemann surface has a very natural embedding into CP2. That's via the so-called canonical embedding. I'll just write as a fact. So every genus G Riemann surface has a natural embedding into CP2. This is called canonical embedding as a quartic curve. In general, the numbers are, you can do canonical embeddings for other curves too. In general, it goes to projective space of dimension G minus 1, and the degree is 2G minus 2. So in this case, G is 3, so G minus 1 is 2. It just goes to CP2, and 2G minus 2 is 4, so it embeds as a quartic. So this is a sign that maybe you can do everything quite symmetrically. So a beautiful observation of Klein in the 19th century was that you can indeed do this and even write the equation of such a curve. Found an explicit equation for such a symmetric quartic. And the equation itself is rather nice. So this one, x cubed y plus y cubed z plus c cubed x equals 0. So it has many symmetries. So the symmetry group G has order 168. So this is equal to 7 times 24. And one can very well think of this as, well, the 7 is because of the rotations of the heptagon, 7 rotations, and the 24 is because you can take any heptagon to any of the other 24 heptagons. Okay. And, well, this 7-fold rotation is more or less visible from this equation, so you may want to see the action on homogeneous coordinates. This is a cyclic group of order 7 acts in the following way. So take a 7th root of unity, then multiply these coordinates with zeta, zeta square, and zeta to the 4, respectively. So zeta here is e to the 2 pi I over 7. Well, one should check that if you do this, the equation is still satisfied. For example, zeta cube and the, so did I do this right? So I think this is not right just because of a simple reason. I should put the cubes on the other one. It doesn't matter, it just changes this ordering of these, but let's do it right. So put the cubes on the other ones, then it should work. So this is zeta here, and the zeta square cube is 6. 6 plus 1 is 7, so that's identity. So then for the second factor, it is zeta squared times 4 cubed, that's 12. 12 plus 2 makes 14. That's a multiple of 7. Again, it's 1. And for this one, it's 4 plus 3 times 1. That's 7 again. So if you start with a point on this curve, after doing this, you are back again on this curve. So you can see this 7-fold cyclic symmetry, for example. But the symmetry group is much larger. It is order 168. You could also write the other symmetries in terms of explicit matrices. It's a little bit harder, but it can very well be done. Oh, maybe another obvious symmetry is the cyclic group of order 3, because if you permute x, y, and z, it's clear that this will go back to itself. What's not so clear on the face of it is the degree 2 symmetries, but you can still write matrices for them too. Okay, now we seem to have gone a little bit too far from line arrangements, so how to go back to line arrangements from here. Okay, now maybe I should say a few more things about this group. So this group G, this has order 168. Well, it's a simple group. Well, let me write this as a product first. This is 2 cubed times 3 times 7. G is simple, meaning it has no non-trivial normal subgroups. And furthermore, it can be seen as symmetries of many things. One way to write it is as PSL2 of the field with 7 elements, but yet another way is to write it as SL3 of the field with 2 elements. And the upshot of writing the Klein quartic is that G is a subgroup of PSL2, PSL3, C. So this last line that I wrote should be seen like the analog of seeing a dodecahedron inside 3 space as rotations, right? So your Klein quartic is sitting inside very, very symmetrically inside CP2. Therefore, it has this group of symmetries which sits inside the group of linear symmetries of the projective space. Okay, now you might approach this group purely group theoretically. For example, you can ask about what its CILO subgroups are, or you could write down the character table. The 3 CILO and 7 CILO subgroups are obviously cyclic because that's the only possible group of that order, right? So order 3 and order 7. But the number of CILO subgroups is something else. You could check that N3 is number of 3 CILOs is exactly 28, and N7, I believe, should be 8. The 2 CILO subgroup is a little bit more elusive, but you can figure out that it's a dihedral group of order 8. And the number of 2 CILOs is 21. Okay, also another thing relevant for us is G has exactly 21 elements of order 2. These are so-called involutions. Okay. Well, we can more or less see the involutions if we use one of these descriptions. This one, the one with SL3 of F2. So this one thing says the symmetries of the projective plane over the field of 2 elements, which is another name known as the phonoplane. So P2 of F2, the phonoplane. So you want to imagine a geometry, projective plane geometry with over the 2 element field. Well, it gives you this familiar picture. We have a total of 7 points on it, and its lines are these sets of triples of points. There's one extra line, if you want a line. The collection of these 3 points is a line. So this is the projective plane on F2, 7 points and 7 lines. And this projective plane has this group G with order 168 as its group of symmetries. Well, the rule is, of course, it should be projective symmetries, therefore incidences should be preserved. So, for example, if you map 2 points to two places, then you are not anymore free to about where you send the third point, because it has to be on the same line, right? So now let me write down quickly the 21 involutions from this point of view. Let's give names to these points, A to G, for example. So, well, one thing you can obviously do is to fix G and try to permute the others. So fix G, and then, for instance, just like mirror reflection as written on the board, you can interchange E and D and simultaneously interchange A and E. So this would give you one involution, just to flip everything like that. Okay. Well, one other thing you could do is to take B to switch B and E and switch A and D and leave the others intact. So that's another involution. And yet another thing that you can do is to take everything to the diametrically opposite point with respect to point symmetry around G. So, for example, C to F, E with B, and A with D. So there are three involutions which fix G, which don't change the place of G. Now, this is a projective plane, so no point is essentially any different from any other. So instead of G, you could have chosen any point as the center. So with other centers, than G, we have a total of 7 times 3, so 21 involutions. Okay. Now, why do we care about involutions? Now, how do your involutions act on CP2? Remember that your group is inside the symmetry group, projective linear symmetry group of the projective plane. Therefore, it should act on CP2 somehow. What are the fixed loci? You can first think about this problem in C cube, maybe on a vector space. If you had an involution on C cube, it's not too hard to see that it must have eigenvalues plus and minus 1, because you know it's minimal polynomial, right? X squared minus 1. So it should fix a plane and a line. Now, in our case, it's not too much different either. You're in CP2, and you can easily show that your involutions fix a line and a point which is not on this line. So our involutions each fix a line and one point which is not on this line. And by fixing a line, I mean pointwise. So you fix every point on this line, okay? You just fix every point on this line, change the others, and there's also one point far away which you fix. Okay, now you have 21 involutions, and that gives you the 21 lines. Okay, so this is the lines of the Klein arrangement promised, so this 21 lines. Now the rest is to figure out how they intersect. And this group theoretical symmetry also constrains how they must intersect. Now, say P is some intersection point of two lines. Suppose they correspond to two involutions, correspond to involutions, let's say I1 and I2. So I1 fixes one of these lines and I2 fixes the other. But then they both fix P. Now I claim that there must exist some other involutions also fixing this point P. And there's a simple group theoretic reason. So these are both elements of order 2. Right, two elements of order 2. And you can look at the CILO2 subgroup which they belong to, okay? It's a D8. All CILO2 subgroups are conjugate and they're isomorphic to D8. And the structure of dihedral group of order 8, well, it has 4 rotations, so it looks something like that. It's like the symmetries of a square, right? Rotate 90 degrees, 180 to 170 and back. And then there are the reflections. So there's one reflection and then S times A square, S times A cube. Now your involutions could be 2 of the order 2 elements. Now let's write down the orders of these elements. This is 1, 4, 2, 4, and all the reflections have order 2. So you have 5 elements of order 2, 5 involutions in this D8. And your I1 and I2 are 2 of them. Depending on which 2, you could have either 1 more or 3 more involutions which fix your P. Which 2 order 2 elements I1, I2 are? There are 3 or 5 elements in D8 fixing P. For example, if I1 is, let's say, A squared in this group, and I2 is S times A, they both fix P, but then the product of these two, which is SA cube, is another element of this group, also fixes P. Whereas for another scenario, like I1 equals A squared, I2, no, sorry, two reflections, let's say, S and SA, then in this case, the whole group fixes P, so all of these elements okay. Now, involutions correspond to lines, so we would expect more lines to pass through this point P than in these two scenarios. But one has to be a little bit more careful because these involutions don't just fix the lines, they also fix one extra point. So if you carefully take that into account, you see that through each point, either 3 of these lines must pass, or in the second scenario, 4 lines must pass. So there are no ordinary points, either triple intersections or quadruple intersections. And you can count their numbers, but you have to do this carefully. So there are 28 such triples. So that gives you T3 equals 28. Or the quadruple intersections, there are 21 of them. So you get the numbers promised in the beginning. Yeah, so this whole story depends a lot on this very special group symmetry, and produces you these numbers. Now, okay, there's one more. Okay, something I forgot to mention. You can say, okay, we had Klein's quartic, and we have these 21 lines. What's the relation? So can you directly relate the lines to the quartic? And it turns out you can. So these lines, 21 lines, are they can be obtained from the quartic with no mention of the group or anything like that. The quartic has so-called polars, and among the polars, where you have to choose a center for this polar, exactly 21 of them are reducible, and they reduce into a conic plus a line. Those lines are the 21 lines of the quartic. That's one other way to describe, which is a little bit more geometric. Okay, now I'll quickly mention this last special arrangement in the list without any verification. That's the Wiman arrangement. And this is even a larger one. This also arises from this alternating group on 6 letters lying inside PSL 3C. So this is even a larger group lying inside PSL 3C. It has 360 elements. This was described by Valentiner in the 19th century. That's A6 really lives inside PSL 3C as a subgroup. By the way, it's a whole interesting discussion. What kind of finite reflection groups you can have inside complex linear groups. And there's a Shepard-Todd classification of such reflection groups. And you can see both groups in their list. Okay, in this case, there are 40. The story is very similar to Klein's story. There are 45 involutions, giving 45 lines. And the intersection pattern of these lines is there are triple, quadruple, and quintuple intersections and no others. And the numbers are 120, 45, and 36. And the other numbers are 0. So they're either triple, quadruple, or quintuple intersections. And it's currently, and as far as I'm aware, an unsolved question whether all these arrangements that I discussed today, so Hesse, Fermat, that was an infinite family, Klein and Wiman, are these all the arrangements with T2 equals 0? So question is Hesse, Fermat. These special arrangements, are these all arrangements with all the arrangements in CP2 with T2 equals 0? Maybe not. Maybe there's some other hidden arrangement or some family even, but nobody knows as far as I'm aware. Okay. Now, to finish today's lecture, I want to at least briefly mention Hirzebruch's inequality. Okay. Now, the motivating question, I guess, although it was probably not discovered that way, that is there a Melchior type inequality for complex line arrangements? Well, Hirzebruch in 1983 found one, and it was later modified. One term was modified by work of Sakai. So it looks like this. T2 plus 3 over 4 T3 is at least as large as D plus. This time you have to start from k equals 5, and T4 term is missing, so 2k minus 9 tk. Well, under the condition that if there are D lines, let's talk about the type B arrangement. And, well, there's a condition. Not an extremely serious one, but still I have to write it. You don't want too many of the lines to go through the same point. Okay, so I mean, this TD not equal to and TD, I just wrote the opposite. I wrote correctly. Okay, so these numbers should be 0. So not all lines should go through the same point, which is dual to not all points being collinear. And a little bit more, you don't want d-1 lines to go through the same point or d-2 lines. So under these conditions, one has to have this inequality. But okay, this is nice. If you look at the special arrangements that we discussed today, you'll see that for the Hesse case and the Klein arrangement, it is just on the border. So it is, you have equality in those two arrangements. So this is sharp. The others also come quite close. And you may ask, okay, does this prohibit any interesting arrangements? It does some. For example, you can show that the phonoplane cannot be embedded in CP2. So a corollary of this inequality is phonoplane, which I drew on the board some time ago, can't be embedded in CP2, so it has some consequences. But one bad part of news is the proof is definitely non-elementary, and actually it's a hard proof. It uses more or less the whole theory of algebraic surfaces, complex algebraic surfaces. In particular, it uses something which is true over complex numbers but not other fields, which is the Bogomolov, Miałka, and Yau inequality for complex surfaces. And as far as I'm aware, there's no elementary proof of this inequality yet. So that's also another challenge. Okay, so maybe I should stop for today.